Hey everybody, Dr. Redsick here with you. This is our second video in 15.7, where we're continuing our discussion of cylindrical and spherical coordinates. Let's get started. What we want to do today is look at a couple of examples and talk more about the decision-making process for opting for cylindrical versus spherical or vice versa, and setting up the limits of integration so that we can start to get a feeling in a practical way for how these coordinate systems work. All right, let's draw some pictures. Okay, so imagine this picture. You got a cylinder like this. So right off the bat, because we said the word cylinder, maybe we have cylindrical coordinates on our minds. Okay, now that cylinder is diameter 2, and there's a hole bored through the middle of it of diameter 1, but see, the hole is off center, so the hole's like this. Okay, so there's this hole bored through the middle, and the hole is off center. All right, so that's diameter 2 and diameter 1. Okay, but that's not the end of the story. Also, we're going to cap that cylinder off with a plane on a 45-degree angle coming in on this picture from back to front. So like this. So that plane's on a slanty 45, and right here and here, that's where the plane intersects the cylinder in the front, and then it intersects it back here. You can't see it, it's obscured. And then this top of the hole is also obscured. And so this right here, this rooftop right here, let me shade that in. This rooftop is on a slanty 45. The floor plan, so to speak, down on the bottom is right here. And so what I'm imagining is a really interesting building where the outside of the building is cylindrical, and then the floor plan on the inside, there's this interior courtyard where there is no roof. So that's that sort of open circle down there in the base. So if you walk into that interior courtyard of this building and look up, you'll see sky out that hole in the rooftop. But if you're actually standing in the red part of the base and look up, you'll see rooftop, but it'll be this slanty roof. It's not horizontal. So that's our picture. Now, if you want the volume of this building, then you're looking for the stuff above that shaded red and below the shaded green. That's what you're looking for. And you can set this up as a triple integral, but we need some coordinate system here. So I vote for this coordinate system. There's y, there's x, and here is z. Now, in that coordinate system, the parts of the base down there in the xy plane have nice polar descriptions. I feel like if we were to try a Cartesian description of the shaded red area, it could potentially be kind of annoying to describe. because for x's that are close to 0, you've got some shaded red, and then you've got the courtyard, so the x's kick out for a sec, and then the x's kick back in, and I don't know, just describing that region down there flat in the xy plane, it doesn't look great as far as x's and y's go, but it looks pretty reasonable as far as polar coordinates in the xy plane go. So this circle here, the outside one, remember this was diameter 2, and in our good old-fashioned polar description of 2D space, flat down there in the xy plane, that one is r equals 2 cos theta. And then the inside one, that circle there, that's r equals cos theta. Okay, so if you want the volume of this and you're going to shoot for cylindrical because you're excited about expressing the base in polar, then the volume should look something like this. V equals, all right, it's going to be some triple integral. To get volume, you integrate 1 dV. Okay, now, in cylindrical, the dV is dz r dr d theta. Okay, so now you got to look down at that shaded region in the xy plane, the base, and talk about the thetas. So if we were to draw that shaded region just in the xy plane, forget about the three-dimensional aspect of this problem for a sec, then just in the xy plane, I think we got this, and we got this, and we got this. That's what we're looking at in the base. And so now you have to describe that in polar. So think about what kind of angles we're talking about in that picture. So you got angles down here like this, and then like this, and like this. So the angles that we have are minus pi over 2 to pi over 2. Now, for each one of those thetas, minus pi over 2 up to pi over 2, let's talk about what r is doing. Well, r starts at the inside curve, which is r cos theta, and r ends at the outside curve, which is 2 cos theta. Now you can bring the three-dimensional aspect into this, because for each choice of r and theta in that base, now z is going to run from 0, flat in the xy plane, up to whatever that slanty plane is. Now, at this moment, we weren't given enough information to tell, so now I'm going to get specific. That was supposed to be a plane slanting down at a 45-degree angle, coming from back to front, and let's say this height here is 3 right there, just to get specific. So let's say this is z equals 3 minus y. So that's the equation of that plane. X is irrelevant, and it's on a slant as far as z and y are concerned. Okay, but though you may want to write for the upper limit of integration right here, you want to say, oh, okay, awesome. So z goes 0 up to 3 minus y. Yeah, that's true. But how is y being described in cylindrical? So remember, in cylindrical, x is r cos theta, and y is r sine theta, because x and y are being described in polar, flat in the xy plane. So z equals 3 minus y, for the purposes of this problem, is z equals 3 minus r sine theta. So now we have it set up. The only letters involved are z's, r's, and thetas. And now we can simply integrate just as we would on any other triple integral. If you're doing the inside integral first, so you're doing, say, this one. Well, that's the integral of 1 dz, so that's z, and then you plug in the limits, and then you do the next integral, say this one. You're going to treat r as the variable of integration and theta as constant, and then you'll finally get to this outermost integral. At that point, you should have only thetas to integrate, and you will do that integral, and that would tell you the volume. So in summary, cylindrical makes good sense on this one because we're dealing with a couple of cylinders, and the description of the base of the object in the xy plane seems to be most suited for a polar coordinates description down there in the xy plane. Okay, so there's an example with setup where we were leaning towards cylindrical. Contrast that with this example. Contrast with this example. All right, same problem. We're going to find the volume of an object. This time the object is like this. You got a big hemisphere, like so. Let's say radius 2. And then nested in there, you got right at the middle, you got a sphere of radius 1 with its south pole just tangent to the base of the big hemisphere. So let's say we got the x-axis coming out like this, y-axis coming out like that, z-axis pointing up like this. And we're trying to find the volume inside the hemisphere and outside the little sphere. Okay, now consider your options. You could do x's, y's, and z's. Okay, so what? Y's vary from -2 to 2, and then x's vary from circle equation with y's in it to circle equation with y's in it. And then z's vary, well, that kind of depends. I mean, if you're here in the base, z's vary from 0 just up to the hemisphere. Of course, if you were tucked in here somewhere in the base, z's would go from 0 until you hit that little sphere, and then they would kick out for a while, and then they would kick back in once you left the little sphere, and then would go the rest of the way to the hemisphere. Okay, I don't think x's, y's, and z's are the ticket. Now, that leaves us with cylindrical and spherical. Now, the base of this region, if we were going to shoot for cylindrical, the base, I think, has a perfect description in polar. The base is just a circular disk. But again, we have that same issue with the z's. If we go for cylindrical, then at locations like right here in the base, the z's are going to be very hard to describe. They're going to start at 0, go till they hit the little sphere, then stop, and then start again when they leave the little sphere, and then go the rest of the way to the hemisphere. And then, if you had a z variation corresponding to that dot in the base, it would be totally different. It would just go 0 to hemisphere. So then you'd have to do at least 2 integrals. I don't know. Cylindrical, despite the fact that the base of this region is a nice solid disk, I don't like the z variation. So cylindrical, I'm skeptical. Spherical, on the other hand, looks like it could be the ticket. After all, this is one sphere nested inside another. So just the fact that we're saying the word sphere kind of points us towards spherical. Furthermore, the description of this 3D object, I think lends itself really nicely to spherical. So here's what I mean. Think about the rho variation in spherical coordinates. So say like down here, flatten the xy plane in every direction, rho just varies 0 to 2. Of course, if you were tilted up somehow, at some angle phi, if you were tilted up at some angle phi, and remember, phi, that's the angle down from the positive z-axis. If you were tilted at that angle phi, then you can see, oh, okay, rho just goes from inside sphere to outside sphere, and that's true at every phi. Rho's variation is just inside sphere to outside sphere. Now, the actual numerical variation in rho totally depends on the phi you're talking about. So, for example, if phi is 0, if you're not tilted down at all from the positive z-axis, then rho just goes from north pole of little sphere to north pole of big sphere, so rho would just go 1 to 2. On the other hand, if phi were all the way tipped down, 90 degrees tipped down from the positive z-axis, then you can see rho, that's this one again, varies 0 to 2. Whatever phi is, the upper limit of rho's variation is 2, and the inner limit totally depends on phi because of that inside nested sphere. So the rho variations are all like this, but they kind of depend on the phi that you're talking about. Now, as for theta, well, this picture goes all the way around. Remember, theta is just good old theta. And so in this picture, theta just goes all the way around. Theta is 0 to 2 pi in this picture. Okay, so what we need to do, if we want the volume of that region, so think about the region here. I'm going to try to shade it in. The region we're talking about right now is this. It's everything in the hemisphere that is not in the inside nested sphere. So this is our region, and we're trying to describe it in spherical coordinates. All right, so we're dialed in on the theta. Theta just goes all the way around 0 to 2 pi. Rho goes inside sphere to outside sphere. So we're going to need descriptions of those two spheres in spherical coordinates. So let's write down a description first for the outside sphere. This one's the easy one. This sphere, well, that's centered at the origin in 3D space of radius 2, so that's just rho equals 2. This sphere, though, that sphere right there, that one's a little trickier. Now, you have some options here. One option is you can write that sphere in Cartesian coordinates. So what is that? That's x squared plus y squared plus z minus a half squared equals a fourth. So x squared plus y squared plus z minus a half squared equals a fourth. So a sphere centered at 0, 0, a half of radius 1/2. So that inside sphere is diameter 1. And that's great, except you need a description in spherical. Okay, so think back to the old polar days. When you were trying to go from x's and y's to r's and thetas in the old polar days, you just, everywhere you see an x, you put r cos theta. Everywhere you see a y, you put r sine theta. and then you would get some giant thing with r's and thetas. Same story here. If you wish to switch from Cartesian to spherical, then everywhere you see an x, you got, what was it? What was the exchange rate there? I think it was rho sine phi cos theta. Everywhere you see a y, you put a rho sine phi sine theta. And everywhere you put, for z, what is it? It was rho cos phi, I think. If you do that and change your good old Cartesian description of that inside sphere into a spherical coordinates description of that inside sphere, it's actually super clean. It's just rho equals cos phi. When the dust settles after all that changing of x's, y's, and z's into their spherical doppelgangers, when the dust settles, you just get rho equals cos phi. So on this one, if you want the total volume, well, you integrate 1 dv. And this time, you know in spherical coordinates, the role of dv is being played by rho squared sine phi d rho d phi d theta. Theta, we decided, that's the blue angle. That goes all the way around 0 to 2 pi. Phi, we already decided, that's the tilt down from the positive z-axis angle. So we got phi values 0 to 90, 0 to pi over 2. And then finally, innermost, for any such choice of theta and phi, rho varies inside sphere to outside sphere. And now we're set. And again, you simply integrate as you would in any situation where you're doing a triple iterated integral, Do the inside integral first. Rho is the variable, everything else is constant. Do the middle one next. Phi is the variable, everything else is constant. Do the outer one last. Theta is the variable. Okay, those are two setup examples of cylindrical and spherical coordinates. These take some practice, they take some careful drawing, and you have to be good at going back and forth between x's, y's, and z's, and z's, r's, and thetas for cylindrical, or rhos, phis, and thetas for spherical. Okay, practice hard. I'll see you in class.